examples of loss. So for squared error loss, the first one is going to look like this. That the x-axis represents theta minus a. And for the second one, the absolute error loss is just the L1 loss. And the third one is LP loss. So P equals 2 corresponds to the first loss, P equals to 1 corresponds to the next, to the second one. And for other P's, you can imagine if P equals to 3, it's going to be steeper than the first one. So, and 0, 1 loss. This one is just a 0 point, a 0 as the original point, and 1 for all other points. And the large deviation loss is something like, it's like a step function. So either theta minus theta hat less than minus c or bigger than c will make the loss become 1. Otherwise, it's 0. And I think you should remember the loss for SVM is something like this.
Epsilon.
Right?
Epsilon insensitive.
And the last one is cut KL.
Function, all of them are positive, except the norm P can also be negative. Yeah. What is the norm P if you imagine P equal to none?
And that's so the last one, KL loss, is just the KL divergence between two distributions. So if theta is a vector, you can compute the loss in this way. So there are two kinds, or you can use these two common use loss. The first one is square error loss, where you just sum up all the components, and the second one is called LP loss. Also, you just sum up the P norm. So some examples. If we want to do some classification, we want to predict y which belongs to 0 or 1. And we have some classifier hx. So we should use 0, 1 loss to compute the error. So it's defined as Lyhx is the number that y not equal to hx. And if for regression, we usually want to predict a real valued y. So now we need to use the squared error loss, which computes the distance between the true y and the predicted y. So what is risk? The risk of an estimator theta hat is computed as the expectation of the loss function. And loss function is just chosen by you. You have several choices, just as mentioned before. And an important thing to notice here is when the loss function is the squared error, this risk is equivalent to the MSE, the mean squared error. So the derivation is here. Does everyone know the variance decomposition of mean squared error? So basically, it's computing the MSE, which is the expectation of the L2 loss, the squared loss. So if we denote M as the expectation of this estimator theta hat, we can directly decompose this to just the two numbers, so we can directly take them out. And, so this term is just number, so we can ignore the expectation symbol. So this one is this term is the bias squared. This term is the variance of theta hat. And this term is 0 because if we just compute the second part, e theta and minus theta hat, it's gonna be e theta of theta hat minus e theta m. While e theta m is just this part, so it's the same term on both sides, so it's 0. So what is this bias variance decomposition used for? So here are two graphs. The first one shows the case of underfitting, and the second one shows the case of overfitting. So here are some properties. So first, an estimator is called unbiased if the bias is 0. So under this case, the mean squared error will become the variance. And usually when we do the training process, there is a trade-off between the bias and the variance. And usually low bias can imply high variance, and vice versa. And in the first graph, it is underfitting, so we have a high bias and a low variance. Actually, the variance can be considered as the complexity of the model you are fitting. So the first one, in the first graph, the model you are fitting is just a line, so it has low variance. So for the second one, you can see it's bump here everywhere, so it has high variance. But for the second one, it fits the data very well, so it has very low bias. So here is mean squared error computation example. Suppose the data x1 to xn is drawn from a Gaussian distribution with mean mu and variance sigma squared. We can estimate the mu and the sigma squared using bar x. Bar x is just the average of all the data points, and the sample variance s squared is computed this way. I think sometimes you may be worried why we are using the sample variance, not the true variance. So I think a lot of people will compute will estimate the sigma squared using something like this. Right? So when there is an n minus 1 term here, so if you use s squared equals to n minus 1 sigma xi minus xi squared, if you take the expectation of this estimator, this one,
sigma squared,
it's gonna be exactly equal to sigma squared. So why people usually use this as an unbiased estimator? So we can see that both these estimators are unbiased, but they have different variance, so different MSE. For the first one, you can compute the variance of x bar is equals to sigma squared over n. For the second one, you can compute the variance of s squared is equals to 2 sigma to the 4th over n minus 1. It is a little hard to compute, but I can tell you some trick to compute this. So for this estimator, another nice property of this estimator is that s squared this is an high n minus 1 squared distribution. The normal distribution. So this is a chi-square distribution. And the variance of this chi n minus 1, well, let's just say chi k square distribution, the variance is 2k. So if you want to compute the variance of s squared, you just need to compute the variance of sigma squared chi n minus 1 squared divided by n minus 1. So you can take the constant out, it's going to be squared. Right? And the variance of chi n squared and n minus 1 squared is just 2 times n minus 1. So it's exactly this, the thing here. 2 times to the fourth over n minus 1.
I have a question.
Yeah?
Does this all work when you assume like you're generating classes of your data? Like your underlying distribution that generates your data?
Generate true data or
does all
generate.
this decomposition of bias and variance nodes only when you assume there's a latent distribution that generates your data?
Can you speak louder?
So all this stuff,
Yeah.
is it true that it only holds when you suppose that there is a latent distribution that
Yeah.
generates your data,
Yeah.
and sometimes you don't know this distribution?
Yes, and you use some estimator to estimate the true distribution, and here comes the bias variance.
But how do you take expectation with respect to this signal that you don't know its form? Let's say for this case, you're
Yeah,
assuming
in
it's a
this
Gaussian
case,
distribution.
we assume that it's drawn from the Gaussian distribution. So we made some assumptions. And if we assume it's Gaussian distribution, then we can compute the mean and variance in this way. If we assume it's another distribution, we will compute it in another way.
But I can assume some other distribution that give me lower variance or whatever. But, right? I can assume it's a different distribution and compute variance like different.
Yes. This is an easy case. If you assume the data is drawn from some weird distribution, some very complicated distribution, then the variance can be very hard to compute. So this is just an example. And theoretically, if you compute the MSE, everything has a bias and a variance. Only sometimes you cannot compute that. It's very hard to compute.
Isn't it true that I just assume there's a variance and there's a mean there, then usually I can compute it without knowing the real form of it?
Yes, there are other ways to compute, to estimate these things. Like if you take the stats class, they will tell you you can use some moment generating function or moment of it can be computed in various other ways. Like so one way is if you know the form, but usually we need to make some assumptions. If you know the form, like the expectation, the form of the first moment generating function and the second moment generating function, if you know the form of them, what I mean is like, so if you know the form for, it's a function of parameters. I don't know how many parameters you have, but you know the form of the first moment generating function. Then you can use all the data, you just sum them up. It will correspond to the first moment generating function. And if you also know the second moment generating function, you can also just sum the xi squared up to and make it equal to the second moment generating function. And it depends on how many parameters you have. Like if you only have 2 parameters, then you have 2 equations you can solve for like theta 1 and theta 2. If you have more parameters, you need have higher moment generating functions. This is another way, and I remember there are a lot of ways to compute this. So you can look at that in the stats class. Okay. So now we want to know from the empirical risk to the truth error. So assume we have data points from x1 to xn. How do you estimate the CDF of this distribution? Well, it doesn't depend on the distribution. I just ask you to compute the CDF, the cumulative density function. How do you estimate that? Well, a simple way is just, let's assume the function is called fnt. So at each point t, you just count how many points fall into the left part of t, fall to that interval. And then you take that part divided by n. It will come out as a CDF of this data. So from Hawking's inequality, we know that this f and t we estimated, how far is it from the true CDF ft? The true ft is here. This is our estimated CDF. So how far are these two things? Hawking's inequality tells us if they are larger than epsilon, the probability of these two things far larger than epsilon is less or equal to 2 times e to the minus 2 and epsilon squared. So this is a very small number. At least it's exponentially decreasing with epsilon, with n. Yeah, they're the same. So this is a nice thing we can say about our estimated CDF. But this is only for one point t. So we would like to know if we do a supreme over all the t's, how far is it going to be? This is a question mark. We don't know that yet. And the same thing happens in classification. So let's assume RH is the true error. So it's
no stories.
Anyone else has an iPad? Oh, it's fine. So let's. So let RH be the number of y not equal to hx. This is true error, so this is error on the test data. And RNH be the number of yi not equal to hxi on the training data. So this is something we want to minimize when we do the training procedure. And Hawking's inequality also tells us that this RNH and RH, their difference is if they are, and the probability of them being larger than epsilon will be less than this upper bound. And we also like to know for all the function h, if we take a supreme over them, how large will it be? Is there an upper bound of it? So why do we care about this? So if this supreme over Rn and Rh holds, if it's smaller or equal to something small, we can say something nice about the training procedure in machine learning. because in supervised learning, we always try to minimize the training error. But and after that, we get an estimator H hat. So how can we expect it will do well on the test data? Equivalently, how small is this RH on the test data? So let H star be the functions that minimize the true error RH. If the following inequality holds, then we can know so H hat is what we got after the training procedure. This H hat is trying to minimize the empirical error. Rn is denoted as empirical error. And this RH hat means if we use this estimator H hat, how well it's gonna do on the test data. So it's a test error using this estimator. It's gonna be smaller than because the above inequality holds. It computes, that inequality computes the difference between the true error and the empirical error. And because this H hat, it minimizes the this RNH function, the empirical error. We know that it's gonna be smaller than H star plus H, right? And
in the same function family? H star and H in the same function.
star and
In the same hypothesis class or whatever.
yes, that's right. Always assume there is a large hypothesis class, big H, and each H is taken from this big H. This H can be finite or infinite. And also because the above inequality holds, we know that this Rn H star is going to be smaller than RH star plus epsilon, also plus this epsilon. So it's plus 2 epsilon. So what did we get from this? We know that if we use this estimator on the test data, the error we're gonna get is gonna be smaller than this one plus 2 epsilon. And this one, because H star, we assume that it minimizes the test error. It's the smallest test error we can ever get. So it's gonna be just 2 epsilon far away from the smallest true test error. So we can guarantee that if we do some training procedure and get an estimated H hat, it's gonna do well on the test data. So the question left is, how can we guarantee that inequality holds? If this big H, the function class is finite, then it's easy to compute this upper bound, because the probability of a union of something is less or equal to the sum of the probability of individual events. So we can get this uniform bound. The supreme over F of this inequality is gonna it's equal to all these events, the union of all these events. So each event just represents for each F, the PNF minus PF, the absolute value is bigger than epsilon. And the union of these events is less or equal to the sum of these, the probability divisibility of each element. And it's going to be less or equal to the sum of, this is a Hopfling bond we get already. And if we sum them up, these are just constants, and we get 2n times the Hopfling bonds. So this part, if you notice, is exponentially decreasing. And this part, 2n, is just a constant. It's going to be finite. So we can guarantee that the whole part, if we multiply them together, it's still going to be very small. Okay. So now we have a nice upper bound if the class is finite. So what if the class is not finite? Which means we are choosing function from an infinite class of functions. So here comes the BC dimension and the shattering, all these concepts. I will introduce all these concepts again. So shattering is just let A be a class of sets, and F is just a set of n points, and G is a subset of F. We say that A can pick out G if A intersect F equals to G. So let SAF be the number of subsets picked out by A. I have some example here. So if A is the class of sets that contain two numbers, A and B, and A must be less or equal to B. So if F is a set of three numbers, 1, 2, 3, then how many subsets can A pick out? Well, it cannot pick out 1, 3, right? Because if it's going to pick 1 and 3, then 2 must be included. So it cannot pick 1, 3. But
there's 1, 3.
oh, sorry. I made a typo. I put some. It should not be here. So, okay, so it can pick out only 7 subsets. What if F equals to 1 and 2? Then A can pick out all subsets, right? So SAF equals to 4.
So why 1 and 3 not?
Oh. Maybe you're
one dimension or 2 dimension?
no, it's just maybe the notation has some problems. What I mean is just for a set, no matter what elements are, the A set is just two numbers, A and B, and A must be less or equal to B. And if we take the intersection of these two sets, we can get the sets picked out by A. So if it,
Smaller than 3.
oh, well, I will give you some examples. So if it's 1, 2, 3, if you make A be 0 and B be 3, what can it pick out? It can pick out 1, 2, 3. Oh,
To do that intersect.
yeah. Let me just make this notation more simpler. So it's 1, 2, 3. What I mean by A is just it's an interval over this one dimension line, and how many points can be picked out by this interval. So it's easy to see that 1 or 2 or 3 can be picked out. The empty set can be picked out. 1 and 2 can be picked out. 2 and 3 can be picked out. And 1, 2, 3 obviously can also be picked out. But 1, 3, it cannot be picked out.
So we are considering one dimension. Yeah? If you imagine that it is in 2 dimensions, and we are using this, so we can take even 1, 3.
There's no sense of smaller.
Yeah, but under this case, it's equivalent to the one-dimension case. It's not the two-dimension case. So let n be the number of points in F. So obviously, SAF should be less or equal to 2 to the n, because the number of all the subsets is 2 to the n. So it's going to be smaller than or equal to that. And we say that F is shattered if SAF exactly equals 2 to the n. So in the previous case, if f equals to 1, 2, then it's shattered by a. And the shatter coefficient is defined as if we take a supreme over f, so f is taken from a large set Fn, which is the set of order, which is all the set of n points. Then, and if we take a supreme over it, over this SAF, we get the SNA. It's the same thing to some concepts I introduced later at USC. And we also have SNA is less or equal to the n. And here is an important conclusion. It says that this inequality we are puzzled about before is going to be, if it's infinite classes, it's going to be less or equal to 8 times the shattering coefficient times some exponential bounds. So this is very nice. So even we don't know the size of this infinite class, we still can use the shattering coefficient to compute this bound. So now we are going to ask, how large is this SNA? So BC dimension is defined as the largest n such that SNA equals to 2 to the n. So, which means D is just the size of the largest set that can be shattered. So for any n points n less or equal to D, SNA is gonna equal to 2 to the n. For n bigger than D, SNA is gonna be less or equal to 2 to the n. But this is not enough because 2 to the n is still exponentially increasing. So for n bigger than D, we still want to know whether there is a tighter bound than this exponential increasing thing. So Sauer's theorem tells us that if A has finite BC dimension D, then this shattering coefficient, this is the same as this one. This shattering coefficient is going to be less or equal to n plus 1 to the D, to D. So now we can conclude that this bond is going to be less or equal to 8 times this thing, and also some exponential bond. So actually, it's not as exponentially increasing as 2 to the n. It's actually the increasing part is in this bracket is n plus 1, and the exponential part is always D. This is a BC dimension already expanded and already determined. So this bond is tighter than the previous bond, that 2 to the n. So here are some examples of BC dimension. So if we have the interval A, B on the real line, then the BC dimension is 2. And the half space in two-dimensional space is the BC dimension is 3. And if we put some disks in the two-dimensional space, the BC dimension is also 3. And if we have convex polygons, just whatever shape you have, but it's convex, the BC dimension is infinity. And this one is the homework question, and you need to think about. I will put a little exercise here. So what is the BC dimension for this thing? It's a point, union, an interval, and the union of points. And they are strictly increasing. So it's a point plus an interval plus a point. So what is the BC dimension of this class? No.
Is it on the real line?
Yeah, on the one-dimensional real line.
Is it 3?
No.
Before answering the question, what do you mean by complex polygons in R2? What is the
line. So it's either this part or that part.
So you mean my
I
data
like-
is gonna be
Convex polygons are something like this.
yes, I know.
Yeah.
What I mean is
Can you see that?
It's not convex.
anyway.
Oh, sorry. It's either gonna be something like this or this or
Yeah. My question is, does that mean that my data is distributed or
they might what distribute?
my data is distributed in this space or what? What do you mean by
Yes.
data?
It means the points you are gonna shatter, the endpoints is
Are
distributed in
distributed.
this space. So the VC dimension for this thing is 4. So does everyone know how to compute a VC dimension? I know the midterm exam asked a question about that. I don't know. Well, actually that one is a very similar to this one.
What's the answer for that?
4 points. So the procedure of computing a VC dimension is just first you have 1, 2, up to n points, and you shatter this set of points until if you have n points you can shatter them, and if you have n plus 1 points you cannot shatter them. Then the VC dimension is just n. So 1, 2, 3 is very easy to examine. It can be shattered by this thing. Now the 4 points. 4 points. You need to enumerate all the possible classes of the 4 points. So it's gonna be 2 to the 4 class, or 2 to the 4 labels of assigning the labels to the 4 points. So 0 points, no points can be picked out, then it can be anything. You just put these intervals anywhere else. And for 1 point, if you want point, then you use 1 minus 1. So 1 means if a point is assigned with a label 1, it means it's picked out, and if it's minus 1, it means it should not be picked out. So for 1 point, you just use either A or D or the interval BC. It can pick out just 1 point. For 2 points, you need to prove for all the points here. So 1 for this point, 1 for this point, or the other 2 points, you need to prove every case. If there are 2 points need to be picked out, you can just use A and D. Just ignore the interval B and C. No matter the 2 points is at what location, it can be here or the 2 points can be something here. The first one and the last one, you can still use A and D to pick out them. And for 3 points, it's the same thing. You can pick out the first and the last point by A and D. You can pick out the middle point by this interval BC. So 3 points, no matter where the 3 points are, it can be picked out by this. And the 4 points is also easy. You just use a large interval B and C. It can pick out all the 4 points. And after this, you need to prove 5 points. It cannot be shattered by this function class. So 5 points, an easy case would be something like this. You want to pick out the first 2 points and the last 2 points, and you don't want to pick the middle point. You cannot use this to do a pickup like this. Right? So, and for any 5 points, there is always a case like this cannot be picked up by this interval. So you prove that for 5 points you cannot do this. So the basic dimension is just n equals 4. So this is the standard procedure to compute a basic dimension. The last part is about Gaussian process. So actually Gaussian process is simple. So if you consider the conditional Gaussian, it's just that if x1, x2, they can be 2 vectors. If they are jointly Gaussian, which means the probability of the joint distribution of x1 and x2, it follows the Gaussian distribution with mu1 is the mean for x1, mu2 is the mean for x2, and the sigma 11 is the covariance matrix for x1, and the sigma 12 is the covariance matrix for x1 and x2, and the sigma 22 is just covariance matrix for x2 itself. If this holds, then the conditional distribution is also Gaussian, which means if we are given x2, the distribution of x1 is also a Gaussian distribution. And we know the mean and the variance of this distribution is this. So the mean is something like this, and sigma is something like this. It's just the linear combination of the views and the sigmas. So if you know about this, then Gaussian process is just the same thing. So assume that we have a lot of data points, and these data points have label y, and this y is real value. And now for a new point x star, we want to predict the corresponding label y star. How can we do that? Gaussian process is just making the assumption that this y and this y star, it follows a joint Gaussian distribution. So it has mean mu1, mu2, and also the variance matrix. The k is just I know something here. So k x star, x prime is just it's like the kernel matrix, and these 2 sigmas are just some noise and magnitude of the. It's just some parameters you can choose by yourself. And this sigma squared is the kernel width, also can be chosen by yourself. And so this k is just a covariance matrix of y itself. So when you have all the data points, you already have the kernel matrix, this k. And this k star is computed between all the data points y and the new data points y star. This is just k star transpose. And k star star is just the covariance matrix by this new point itself. So because the joint Gaussian follows this this formula, we know that given all the data points and their label y, if we are given a new data point x star, we know that the y star should follow the Gaussian distribution, and we know its mean and its variance.
So this is y is cellular, and we can compute that from the features for the x.
Yes. You have some x. This x is
how does that kernel matrix deal with, how is that related to anything above?
Oh, this K is the K defined above the first equation. The covariance matrix is K. Is defined as this.
But that's like an equation of two variables, and the other one is a matrix. Is that right, or?
Yeah. If you let's just assume there are 3 points, y1, y2, y3, and x1 is a vector. Okay, it's feature vector and features defined by yourself, and x2 also is a vector. So it just tells you that so the Gaussian process makes the following assumption: is that y1, y2, y3, and if you want to estimate a new point y star, here, it follows a Gaussian distribution where the mu is there is a mu for these 3 points, and there is a mu star for this y. Actually, in standard Gaussian process formulation, these mu are defined as 0, so this is just 0. And the covariance matrix, this is what's important. So you can imagine there is a 3 by 3 matrix at this corner, and you have a number here, a number here, a number here. And this 3 by 3 matrix is just computing the distance between all the vectors. So for example, this is K. K11, K12, K13. For example, K12. K12 is computed using that formula, where the x and x prime is replaced by x1 and x2.
Okay, so it's a grand matrix for the.
Yeah.
Okay.
So actually, these could be vectors, not just numbers. It's x and x prime. Oh, K star is just a. This is not a number. This is a
3 by 1.
3 by 1 vector, where each number here is computed between xi and x star. So here, this is also a 1 by 3 vector. Okay. Actually, Gaussian process.
How do you pick how do you pick your covariance matrix?
It's computed in this way. It's a standard formulation.
Can you substitute any kernel you want there instead of just the RDF kernel?
What did you say?
So that uses an RDF kernel, right?
Yes.
So you can use any other kernel you want.
It's Gaussian process.
I think it's called Gaussian process. It should use an RDF kernel.
Not necessary.
All the materials I have seen, they are always using an RDF kernel. I don't think any material ever uses a linear kernel or something.
But as long as it's positive, that everything works.
Yeah, that's the definition for kernel matrix, but I think here you should use an RDF kernel.
Or derivations and conditional stuff. The inverse stuff doesn't ever mention what this case are.
Yeah, I think for a kernel matrix, you can use whatever kernel as long as it makes a positive sign definite matrix. Yeah, but here, because for all the materials I have read, they are always using this RDF kernel. I don't think you can ever use other kernels.
the delta? Delta xx?
Actually, this sigma squared n is the noise. So they make the assumption that the noise is only there independent along different data points. But for each data point, it has varies for itself. So this delta is just means if x equals to x prime, I add a sigma squared as the noise. Otherwise, I don't add it. So it's equivalent to saying that the noise matrix follows Gaussian distribution with mean zero, and the variance is diagonal matrix with sigma n squared all over that.
Okay, so it's 1 if x equals x prime and 0 otherwise.
Yeah.
Okay.
So if you didn't, how do you pick mu2? How do you pick mu2? How do you determine mu1 and mu2?
Yeah, this is determined by yourself, and the standard formulation for Gaussian process, mu1 equals to 0 and mu2 equals to 0. So it makes things simple.
But like if you look at that power distribution, if you change mu2, you actually change a lot. Right? So you can shift by
Yes,
whatever
if you
point.
have some prior knowledge, you can use mu1 and mu2 with values you have chosen. But if you don't have any prior knowledge, you can just use 0. It can work as well.
If you, like,
Yeah, I know if you choose different numbers for mu, you can change the answer a lot. Yeah, you can do that. Because mu1 and mu2 are chosen by yourself, you can use whatever method to compute that. It depends of how confident you are with your prior knowledge. So if you have enough prior knowledge, if you are pretty confident that mu1 should equal to x star, then you can just use x star. Otherwise,
The average of it.
okay, if there are multiple x star, yeah. So the last part is about Gaussian process classification. So we also receive x1 to xn, and also all the corresponding labels y. But now y only takes value from -1 and +1. So can we again assume that y and y star follow this Gaussian distribution? We cannot, because it's discrete value and it's discrete value, not continuous anymore. So we cannot assume a Gaussian distribution. So can we connect this with previous results in regression? So the solution is we add a pseudo label Ti. This Ti is continuous just as the Yi before in the regression. And for each Ti, we add a model from this Ti to Yi. It's just a sigmoid function. So if you draw that, the curve of that function is just something like this. And now we can still assume that T follows a Gaussian distribution.
If you're somehow considering that your x data has the Gaussian distribution,
X data?
yeah, I mean, you are doing a classification, you have some x and y. When you are classifying, you are implicitly saying that your x data has a Gaussian distribution.
Yeah. with the covariance matrix computed from all the axes. It's the same thing as before, only now I add a model here from how can we compute from Ti to Yi. So Ti is continuous while Yi is discrete. So we add a sigmoid model here. The probability of Yi given Ti is just a sigmoid model computed in this way. So, okay.
Is there any reason to use a sigmoid model?
Yeah, because you have taken the class of neural network and logistic regression, right? So this is a very common function from making a continuous label to discrete labels. So if you consider about this function, it has a very small threshold here. Because you don't actually care about how large is x or how small is x. You just care about when it reaches a certain threshold, this function should directly output a 1 for you. And if it's a little smaller than some threshold, it should predict 0 or minus 1 to change function. So this is commonly used because this the function between this part is very steep. So, and people don't want to use a step function like this, because you may ask, why don't you use just a step function?
Continuous.
Because this one, it doesn't have a derivative at least twice. So a sigmoid function is much nicer than this one.
So one more question. This is how you get Yi from Ti, right?
Yeah.
How do you get Ti from Yi? Isn't that
This is hard.
right?
That's why we don't do this.
Alright.
So, so now after we assume T, we just need to maximize this probability. After seeing Y and X, we want to maximize the probability of T. So it's proportional to PT T given X times PY given T. And this PY given T can be decomposed for every individual labels. So the first one is the Gaussian distribution, so it's just the exponential part, that part. And I ignore all the constants. And then the second one is just the sigmoid model, as defined before. So equivalently, we want to maximize this log likelihood. And it's equivalent to minimize that minus 3. And if we minimize that, we can get a T, a vector of T, which is continuous. So it's like we have all the data points X, we have all the discrete labels Yi, and now we get Ti for each data point, and it's continuous, which is exactly what we need to do regression, the Gaussian process regression. So again, we repeat the procedure of Gaussian process regression because we assume these two follows a jointly Gaussian distribution, and we can compute T star from all the T's using this formula. And after we get this T star, so for this new point X star, we get a continuous label T star, and we can predict Y star using the same model we introduced before.
What's the difference between just use like sort of kernelized or just regression, like 1/1 plus e to the negative of the transpose x, then you have
E to the minus what chance?
so you just feels like you have a you first map it to so you assume like there's a latent continuous value. But you have a logis regression operate on it, and you
Yeah.
get the label, right?
Yeah.
And then you want to maximize some sort of configuration of this T.
Yes.
But you can do directly, like, if you really want to kernelize it, it's like you would still assume just regression. It's 1/1 plus e to the power of negative W transpose x. And then you just use W transpose x and use that W as a kernel expansion. That still works, right?
But that's not Gaussian process anymore, right?
But you have like two levels things, which sounds weird.
Yeah, you can implement that method and compare the result with Gaussian process and see.
And I'm like not convinced by this prior rule statement. Rule and mu2. Just you can change mu2 and scale all the things.
Yeah, in the homework actually you are going to implement the Gaussian process. So at that time you may want to choose different values for mu and see how it affects the result.